We are the controls engineering team for the Themed Entertainment Association at Notre Dame, presenting Thunderbird's Tempest, a fully functional ride and show control system. This project utilizes real industry software and programming languages to safely control a swinging pirate ship-style model theme park ride, which will soon be ready to construct. A PLC, or Programmable Logic Controller, is a rugged industrial computer designed to control machines. They were first developed in the late 1960s to replace massive relay-based control systems in factories, making automation faster, more flexible, and easier to modify. PLCs run almost any industrial process you can think of, but over time, their ability to run continuously for years led to their adoption within the theme park industry as well. However, building control systems with traditional industrial hardware can be extremely expensive. A single PLC can cost thousands of dollars, with I/O modules adding hundreds more per unit, and software licenses for major manufacturers often costing several $1,000s on top of that. So for our project, we set out to recreate that same industrial control architecture, but with more accessible hardware and software. Instead of a traditional PLC, we use a Raspberry Pi as the main controller, supported by Arduino microcontrollers handling distributed I/O. Using affordable components, we're still able to implement the same core structure used in real industrial systems. In our setup, sensors, buttons, and actuators exist out in the field, interacting directly with the physical ride system and the ride operator. The Raspberry Pi acts as the PLC, processing inputs and making real-time control decisions. And on top of that, our SCADA HMI provides a live bird's-eye view of the entire control system, allowing operators to monitor system states, respond to alarms, and control the ride from any device.
To program the control system, we wanted to stay as close as possible to real industrial standards by using the official IEC 61131-3 PLC languages. We achieved this by using the open source platform OpenPLC. Development was done using the OpenPLC editor on our laptops, while the OpenPLC runtime was deployed on the Raspberry Pi to execute the compiled control logic. OpenPLC provides all the primary features found in most brand name PLC editors, like live debugging, while also being able to handle function blocks with all 5 official PLC languages, as well as Python and C++. At the center of our system is this function block diagram, which provides a high-level visual representation of how the ride operates. All of the core function blocks within this diagram are written in traditional PLC ladder logic. We use custom user-defined data types to represent the state of the ride, such as stopped, waiting, or running, and trigger these state changes based on the sequence of Boolean logic in the ladder diagrams. For more advanced operations limited by ladder logic, such as changing the state of our ride, we utilize functions written in structured text. Altogether, this system manages key ride behaviors, including emergency stop recovery, stepper motor homing, manual motor jogging, and controlling a full ride cycle with synchronized lighting and audio. To handle audio playback specifically, we also implemented a Python-based function block, which triggers different sounds to play over Bluetooth to a speaker.
Hold on tight, Storm Riders. Keep all hands, arms, and legs inside the vehicle at all times. Welcome back to Solid Ground, Storm Riders. We hope you survived the Tempest! Attention, Storm Riders. It seems Thunderbird needs a moment to recharge. Please remain seated, keep your lap bars down, and hold.
To expand beyond the limited I/O available on the Raspberry Pi, we integrated an Arduino Mega as a Modbus RTU slave device. This allows the system to communicate over a USB cable and effectively extend the number of inputs and outputs available to the control system. This remote I/O layer is responsible for interfacing directly with the physical system. It receives inputs from buttons on the operator panel, limit switch signals, and feedback signals from the motor and LED controllers, sending that data back to the Raspberry Pi for processing. Based on this input, the OpenPLC runtime sends commands back through the Arduino to activate relays for our operator button panel LEDs, our e-stop motor driver power circuit relays, and signal to our motor controller and LED controller what PWM signals to send to the stepper motors or LED strips. To create a web-based user interface for our control system, we configured an OPC UA server within the OpenPLC runtime. OPC UA is a widely used industrial communication protocol that allows different systems to securely share real-time data. Through this server, we exposed important tags from our PLC logic, such as the current ride state and the remaining time left in a ride cycle. To build our HMI, or human-machine interface, we used the free Maker edition of Ignition by Inductive Automation, which functions as a full SCADA platform for monitoring and controlling industrial systems. We set up an Ignition gateway on a separate computer and established an OPC UA client connection to the Raspberry Pi by specifying the OpenPLC runtime's IP address and port number. Once connected, all exposed PLC tags became available within Ignition, allowing us to monitor and interact with those variables in real time. Using the Ignition Designer, we developed a fully customized web-based HMI, and because it runs in a browser, the interface can be accessed from any device on the same network. The HMI displays key system information, such as the ride's current state and whether it is in maintenance mode. It also allows operators to write values back to the PLC. For example, toggling house lights on and off. We leveraged browser-based rendering and custom CSS with Ignition style classes to create animations. This includes a rotating pirate ship and animated storm clouds. These visual elements are triggered by linking tags to certain properties and creating a transformation, like this one that displays the ride state and changes the background color based on the tag's value. In some cases, we used Ignition's Python scripting to link certain events, such as mouse triggers, to reading and writing new tag data. An alarms table was also created along the bottom of the HMI, which provides operators and maintenance teams with a timestamp, an alarm priority, and suggestions on how to clear the alarm, as well as the ability to acknowledge or shelve recurring alarms. For example, the emergency stop button is configured as a high priority alarm, requiring a defined recovery process before operation can resume. More severe system faults are classified as critical alarms and indicate that actions such as motor rehelming are required. Looking forward, this system can be expanded by integrating a database to log long-term system data and trends. Ignition also supports alarm pipelines, enabling notifications to be sent to operators or maintenance teams via platforms like Slack, email, or SMS.
Now onto a closer look at the electrical system. All components were mounted on DIN rail, which is a standardized industrial mounting bar used in most electrical cabinets. Our control system needs to power mostly 5-volt devices such as our Raspberry Pi and Arduinos, but also needs to power two 24-volt stepper motors. To distribute this properly, we start with taking a 120-volt AC from a wall outlet into an extension cord and connect this to our AC to DC 24-volt 20-amp power supply. That power supply's 24-volt output is connected to a power distribution fuse block, which branches off to our two 24-volt stepper motors, as well as a 24-volt to 5-volt 10.8-amp DC to DC converter. The 5 volts then branch off to another power distribution fuse blocks, which powers our Raspberry Pi, 3 Arduino microcontrollers, LED strips, and our operator button panel indicator lights. One of the Arduinos acts as a Modbus RTU remote I/O slave device connected to the Raspberry Pi PLC through a power blocking USB port. This Arduino effectively expands the available GPIO of the Raspberry Pi, which it uses to send commands to the 2 other Arduinos. One of these other Arduinos acts as the stepper motor controller, creating PWM signals that would be impossible to create with the 20 millisecond cycle time of our PLC. The third Arduino acts as our LED strip controller, similarly handling complex PWM signals based on the states set by the PLC. The remote I/O Arduino handles receiving signals from the 6 push buttons, 1 emergency stop button, and maintenance key switch from the operator panel. It also sends signals to turn on and off the 7 indicator lights. Directly connecting these industrial indicator lights would exceed the current capacity of the remote I/O Arduino GPIO pins, so we use a set of solid-state relays to open and close the individual LED circuits from a separate 5-volt power branch. The most critical part of the system is the emergency stop circuit. The ride uses one stepper motor to drive the pirate ship itself, while a second actuator motor physically moves the drive wheel into and out of contact with the ride. In the event of an emergency stop, power must be immediately removed from the drive motor, while the actuator motor retracts the drive wheel, allowing the ride to safely coast to a stop. The action of cutting power from the drive stepper motor is handled by these two electromechanical relays. They are placed in series, so power has to pass through both of them in order to allow the drive motor to turn on. Our physical e-stop button is hardwired directly into one of these relay modules, as well as the PLC itself. The second relay is controlled by the PLC through what we call the program stop output. This architecture gives both the operator and the PLC independent authority to disable the drive motor and stop the ride. It also allows the system to enforce a controlled recovery procedure before the ride can resume operation. After an emergency stop occurs, whether triggered by the operator or by a detected system fault, the ride must first be placed into maintenance mode by maintenance personnel. They are then required to cycle the physical emergency stop button in and out to verify the correct functionality and detection of the e-stop button. Once this is complete, the reset button can be pressed, which initiates the actuator motor homing sequence. Once the actuator reaches its limit switch and confirms the correct position, the PLC releases the program stop relay and allows the ride to be switched back into automatic operation. If another emergency stop occurs, the entire recovery process must be repeated before operation can continue.
At this stage, the Thunderbird's Tempest control system is fully operational and ready to be integrated into the actual ride once mechanical construction is complete. Throughout this project, we learned a tremendous amount about the software and hardware tools used in real ride control systems, and we hope this project helped introduce some of those technologies to you as well. From all of us at TEA at ND, thank you for watching.